Hi, in this video we will be discussing a different tool that can be used to find relationships between variables. So far we've discussed chapter 10, which is about two population hypothesis test, and chapter 12, which is about one-way or single factor analysis of variance. Now we move on to chapter 13, which is about chi-squared test for independence, and as we can see in this matrix, this test is used for us to try to identify if a relationship exists between two qualitative variables. So in chapter 13, we have this concept called the chi-square test for independence. Now chapter 13 from the textbook is actually longer because there are lots of other applications of the chi-square test, but we will be focusing on the use of the chi-square test to test for independence between two variables. So again, this is used to find if there's a relationship that exists between two qualitative variables. And since this is also a hypothesis test, we have a null and an alternative hypothesis. And here, the null hypothesis for the chi-square test states that the variables, the two qualitative variables, are independent. And for the alternative hypothesis, it states that the variables are dependent. Therefore, the variables are related. So, to determine if the variables are dependent or independent, we will have to compute for what is called an expected value. And the expected value is simply the total of the row times the column total, and then divide that by the total number of responses. So this is the formula that we will use to compute for the expected values later. Okay, and since we are trying to test relationships between two qualitative variables, as discussed from chapter 2, the best way to present information about them is through a contingency table, or a cross table, or a matrix, or a pivot table. So we will have to present data first in the form of a contingency table, and after that we can compute for the expected value, and then later on we will be able to make interpretations. Now, the chi-square test for independence is valid if certain assumptions are satisfied or certain conditions are satisfied. So for chi-square test for independence, the fastest way to check if you can perform the test or if the test is valid is if all expected values that you were able to compute for are at least 5. So remember the formula shown earlier. You have to compute for this for all intersections or for all values in the table, and then if all of those expected values are at least 5, then it's valid to perform the test. Now, if ever not all expected values are at least 5, it's still possible for us to perform the test, or it's still possible for the test to be valid if 3 conditions will be satisfied. So here, all the 3 should be satisfied for us to be able to perform the test. The first one is slightly more lenient as compared to the first one. Instead of having all expected values at least 5 here, the minimum is for all expected values to be at least 1. Also, the number of cells should be at least 5. Therefore, if this is a contingency table, then you are supposed to have at least a 3x2 table, because if you just have a 2x2 table, a 2x2 contingency table, then you only have 4 cells. So again, under this alternative test, you have to have at least 5 cells. And finally, if you get the average of all the expected values that you computed earlier, the average should be at least 5. So if all of the 3 conditions here are satisfied, then it's valid to perform the chi-square test of independence, and then later on, we will be able to make an interpretation. Okay, so now we will try to perform the chi-square test for independence using Excel. Now, we don't really need the data analysis toolpack nor StatPlus for us to perform chi-square test for independence, because it's actually native to Microsoft Excel. So we don't really have to use complicated tools, because we have actually a function inside Excel that can compute for the p-value. So let's say we are interested to test if there's a relationship between times visited and the monthly household income. So we have here the database for Bark and Blend. So again, same process. I'll copy this variable to another worksheet. And then the other one is monthly household income. Okay, so now that we have segregated or isolated the 2 variables to another worksheet, again, as discussed earlier, the next step is to compute or to present this using a contingency table. So again, ideally, for a contingency table, you place one variable, for this case times visited, to the row or to the column, and then you do the same for the monthly household income. And a fast way for us to do this is something that you should have discussed from ITM 11, is through the concept of the pivot table. So for Mac users, just highlight the two columns and then press theta and then press pivot table. For Windows users, that's going to be highlight the two columns and then go to insert and then insert the pivot table. So here, I'll be selecting this. That will be my range. And then I'll just paste the pivot table in the existing worksheet, and I'll just put it here. And then for us to have the actual table, I'll be dragging certain variables to certain parts of the table. So in this pivot table builder, I will drag monthly household income to the rows, and then I will drag times visited to the column labels. And then for the values, for us to have the values inside, you can choose any of the two and then drag that to the values. So I'll be choosing times visited, drag that to the values, and now I have this pivot table. So it now shows us the frequency for the different intersections. Now for Mac users, we can actually just perform the computations now. But for Windows users, I think you have to copy the entire table first before you start making any computations. So to do that, just copy the entire table, paste it to another place, and then you can now start computing for the expected values. Okay. Now the formula for the expected values were shown earlier. So we have the column total times the row total over the total number of responses. Now we need to compute for that expected value for all of these intersections. So we have 3 by 5, which means that we have to compute for 15 different expected values using the same formula. Okay, and to compute for that, we can just use the functions here in Excel. So again, that's column total times row total, and then divide that by the total number of responses. Okay, so if you look at this function, it computes for, again, column total times the row total, and then divide that by the total number of responses. And I have to do that computation for all the 15. So for the next one, the column total is now 40, and then multiply that to the same row total, which is 24, and then divide that by the total number of responses. Okay, so again, you just have to do that for all the values. And if you recall from ITM 11, we have the concept of absolute and relative referencing. So that's the use of the dollar sign, so it will actually make the computations faster. So here, I'll try to add a dollar sign before 17, row number 17, so that even if I drag the formula downwards, then the value will still be 30. And then I'll multiply that to the row total, but here I'll add a dollar sign before each, so that even if I drag the formula to the right, then this will still be each. And then divide that by the total, so both dollar signs before the row and the column, because regardless of any computation, the total will still be 100. So if you do that, I think it will be faster for you to make computations. And even if you double check the functions, you see that the values that were used to the computation are actually correct. Okay, and now that we have expected values, the next step is now to test if it's valid, to see if it's valid. And again, as mentioned earlier, a fast way to know if it's valid to perform the test is to just check all the expected values if all of them are at least 5. But as we can see here, there are some expected values that are equal to 3, some are 4, some are 3.9, and again, not all of them are at least 5, which means that right now it's not yet valid to perform the test. But again, we have another way to check, and that is through the 3 conditions. So the first one is to check if all the expected values are at least 1. And as we can see here, all of them are at least 1, so the first condition is satisfied. Now the next one is to determine if you have at least 5 cells. And here, we actually have 15 expected values. So again, the second condition is satisfied. And finally, the last one is to check if the average of all the expected values is at least 5. And highlighting all these expected values, you can see here that the average is indeed greater than 5, which means that the test is valid. Okay? So now that we've tested the validity of the chi-square test or validity of the data, then we can now use the chi-test function in Excel to determine the p-value. And to access the function, just type in any cell equal sign chi-test. So this is an Excel function, and then for this function we need two arguments. We need to make two selections. So the first one should be the actual range, so the actual frequencies, and the next one should be the expected range. So for the actual range, I'll be highlighting all the all the actual values or all the frequencies from the original pivot table, and then type comma so that we can proceed to the expected range. And now I will be highlighting the expected values. Okay? And once you're done making the selections, if you press enter, the function will provide you with the p-value. And once you have the p-value, then it will now be easier for you to make the interpretation. Just compare this to alpha, and if the p-value is less than alpha, then again, you can reject the null hypothesis. So here in this problem, the p-value is 0.0069. This is less than 10%, 5%, and 1%. However, this is greater than 0.1%. So it means that we have very strong evidence to support the claim that the qualitative variables, times visited and monthly household income, are dependent or are related. Okay, so again, because the p-value is less than 1% but greater than 0.1%, we have very strong evidence to support the claim that the times visited of the customer of the establishment is related to the monthly household income. So that's how we interpret the results of the chi-square test. Now, be careful when performing the test. Here, the chi-test will only give us a correct will only provide us with the p-value if the number of cells highlighted for the first one, for the actual range, is equal to the number of cells highlighted in the expected range. So if, let's say, you made a mistake, instead of 23, your selection was something bigger, one row bigger compared to the original one, then if you press enter, it will give us an error, because again, the number of cells do not match. So you have to make sure that the number of cells highlighted for the actual range should be the same as the number of cells highlighted for the expected range. Okay, so that's our first example. Now, let's have one more. Let's try to test if there's a relationship between the age and the times visited. So again, here we have age and times visited. So just copy the two and then paste that to another worksheet. Now again, normally age is considered quantitative, but again, the problem here is that the age is considered qualitative because we have different ranges instead of the actual values. So since this is now qualitative and then times visited is also qualitative, then we have to use chi-square test for independence. So once you have the two variables isolated, so come up with the pivot table to come up for us to be able to compute for the expected values later on. And then I'll be pasting that to the same worksheet here. Now you can place any. Okay, so for me, I'll just place age in the rows. I'll place times visited in the columns and then choose any of the two and then paste that to the values. And now we can see that we have the contingency table. So again, for for Windows users, you have to copy and paste the pivot table so that you can use the values here for some computations. Okay, so now that we have the pivot table, we can now compute for the expected values. Again, we use the same formula. That's the column total times the row total over the total number of responses. And then do that for all the cells in your pivot table. So again, this is 3 by 5, so we have 15 expected values. Now again, once you have all the expected values, then you can now try to test the validity. First, as we can see, obviously not all expected values are at least 5. Okay, in fact, we have here 6 expected values that are less than 5. So again, the first test, the quick one, is not satisfied. Now again, another way to test if it's valid to perform the test is through the 3 conditions. So first, are all expected values at least 1? Unfortunately, here in this case, we have two expected values that are less than 1. Okay, which means that even for the alternative test, it seems that the test is invalid. Okay, so what does that mean? The test is invalid because you don't have enough responses, and the best way for you to fix this, or to make the test valid, is for you to get more responses, so that hopefully all the expected values will be at least 1 and the two other conditions will be satisfied. Okay, but here let's say you don't have enough time to gather data anymore. There's actually one other way for us to try to fix this, and that is through combining certain rows or certain columns. Okay, and if you look closely at the expected values, the problematic expected values are found in row 2. Okay, that's for greater than 33, and that's because you only have 3 responses for age group greater than or equal to 33. So a good way for us to fix this is to combine this to another column, or to another row. Okay, but we know that we can't really combine this to any other row, or we can only combine this to something that's next to it. Okay, so it's illogical to combine less than 16 and then greater than 33, because they are very different. So the best, or the only way for us to combine this is if we will combine this with the next interval to it, which is 28 to 33. So we will transfer all these frequencies for greater than 33 and then transfer that to 28 to 33. So let me just delete this, and then now I'll copy the table again, but here this one will transfer this to this. So this will now be 6. Okay, so this will now be deleted, and then 1 will be transferred again to this row. Okay, so again this is now 0. So what happens now is that we remove that row greater than 33, and then this row is now changed. So it's no longer just 28 to 33, but this is now greater than 28. So we still have 100. Okay, the total for the columns are not affected, but here the total for the row will now change. So earlier it was 18, but since we transferred 3 to that row, then it's now 21, and then everything else is the same. Okay, so now that we've combined the two rows, then maybe we can now test if the test will be valid. So again, same formula: column total times row total over the total number of responses. Okay, so again, you can double check, press other functions to see if you type in the correct formula. And then here, we can now see that the expected values that were less than 1 were now eliminated. So maybe we can now check if the tests for validity are satisfied. So first, are all expected values at least 1? Yes. Okay, so the smallest is 1.2. This is now greater than 1. So the first condition is satisfied. Next, we should have at least 5 cells, and now even if you removed one row, you still have 12 cells, so the second condition is still satisfied. And for the last one, the average of the expected value should be at least 5, and now the average is 8.3, so that is still again at least 5, which makes the test valid. So we can now use chi-test to compute for the p-value. So again, the first selection should be the actual frequencies, and then followed by the expected values. And then computing for the p-value gives us a p-value of 0.1161 or 11.61%. And now that we have the p-value, we just have to compare this to the different values of alpha. And clearly, this p-value is greater than 10%, 5%, 1%, and 0.1%. Therefore, following the same process for hypothesis testing, we do not have enough evidence, or there is insufficient evidence to support the claim that there is a relationship between the age group and the times visited for the customers. Okay? So that will be the interpretation for this test.